dependent on these amplitude, but rather instead of that 1 point pulses, it is basically smearing at the x-axis. So that means if you increase the signal energy, that means if you increase the EB by N0, keeping N0 fixed, EB you are increasing. That means I am increasing the input power. So it doesn't matter, and that you are observing. That you are observing here. Even if you are increasing the probability of bit error, that is not reducing. Even if you are increasing this signal to noise ratio, EB by N0, but this probability of bit error, it is not moving like this. Okay. So this is, that means more signal to noise ratio may not help the ISI problem. May not help the ISI problem. Now that, so for that, what do we do? Generally for ISI, we do the Nyquist pulse. That means Nyquist pulse means, if you can remember, that means for Nyquist pulse, what do we do? Usually we generate, say for this type of pulses, we have this type of Nyquist, this rectangular system. That means it is a rectangular transfer function, which is basically for the bit rate is the symbol rate is t samples per second. That is t samples, yes, in 1 second between two. Here you are sending one symbol. Here you are sending another symbol. So that means the gap is t second. So that means t number of samples you are sending in per second. So that means per second t samples you are sending. That means, or rather, if you say t symbols per second. Here, what about the bandwidth? Bandwidth is upwards. That means it is like that. Rather, if you say that it is, if you say t equal to 2, or rather t equal to say half, then t equal to half means 2 symbols per second. 2 symbols per second. Then the bandwidth is 1 by 2t. That means 1 hertz. Okay, that means for in a channel so that means for 1 hertz channel you can maximally send 2 symbols per second. But we have seen, that means we have done, that there is some problem of this type of sync pulses. That means if there's a timing jitter, then normally with the Nyquist pulse we have seen that it is at this timing there is no effect of the previous one. That means only it is the effect of these pulses. So similarly at this point it is the effect of these pulses. No other pulses are present. When you are sampling it at this point, then the next pulse is basically zero crossing. The previous one, if you see, that means if I do sampling over here, if I do a sampling over here, then what will happen? It will be crossed like this, and it will also cross like this. Okay. So that is fine. So that means as such HF, that Nyquist, if I just send that sync pulse, then it is fine. But the problem is, that means if there's a timing jitter, then you have a problematic, because the damping of the sync pulse, that is not very high. That means it has, so instead of at this point, that means if you instead of this point, if you do the sampling over here, then you will find, or rather sampling over at this point, you will find that I have some effect over, say, at this point, that is that instead of 0, if you do the sampling at t by 2, or maybe at even at t by 4 also, you will have a huge component of the previous one. So in order to mitigate that, what we have done, that means we want a fast decaying kind of pulses. We want a fast decaying, instead of sync, we want a fast decaying pulses. Something like this. Okay. So in order to do that, what we have done, that we have just removed the restriction of our this bandwidth. Rather, we have increased the bandwidth, and that actually comes to the raised cosine filter. If you can remember from the other book we have studied, this was our basic pulses with sync one. With sync. Okay, so and here it is something like that T, then bandwidth was 1 by 2. That we have started. That 2 symbols per second is 1 hertz. Okay. Now rather I am saying, I am just relaxing the bandwidth because this is the minimum bandwidth you have to. Rather we are saying no, we will not operate on minimum bandwidth. We will go for some sort of a higher bandwidth. So depending on that rule of factor, that is, if you can remember, that is this is R equal to 0, R equal to 0.5, R equal to 1. And when I make R equal to 1, my bandwidth is the double. Instead of 1 by 2t, it is 1 by 2. Okay, and when we have a, and also you see these the frequency domain characteristics depending on R 0.5, R 1, they are all raised cosine characteristics, and the point is that depending on R equal to 1, R equal to 1, for R equal to 1 where you are using the double the bandwidth, at this point this damping is very high. You see, that is when R equal to 0, a pure sync, it has a huge gap. That means if you do the, if you have a timing jitter problem, that means that at this point, that means if I just miss at this point, then you have a huge error from the previous one or the post one. But if I have a R equal to 1, that means as the damping is high, instead of this point, when I do the sampling at that point, that equal to, that means I have this type of characteristics. Okay. Now at this point, even if I little bit away from the current point, so it will reduce from here. But the effect of the previous one, for pure sync it is this much, but for R equal to 1, this is only this much small. Okay. So that this we have studied, and this filter, that means if you remember that raised cosine characteristic, that HF is some sort of a cos square some term, and that excess bandwidth is W minus X, roll of factor is the excess bandwidth divided by the nominal bandwidth, that is W minus W0 divided by W0. That means, say this is your W0, this is W minus W0 means 2. W is R equal to 1 means W minus W0 by W0 equal to 1, that means W equal to 2W0. Okay, that is W equal to 2W0. That means R equal to W minus W0 by W0 when R equal to 1, that is W equal to 2W. That we have started. So this is called raised cosine filter, and if you do this operation in the time domain, you see that I have a sync, normal sync, but also I have some cosine case. Okay, this you have already studied. Now let us see this effect. Okay, so these tests, so that means if I have the raised cosine filter, the basic point is that, so if I have a raised cosine filter, say with this type of characteristics, or say this type of characteristics, this is not only it will have a zero crossing, it will have a zero crossing at 0 TB, 2 TB, it's minus TB, all this point. That means at this point, all I have the zero crossing, because if, say this one I am transmitting 1, then say 0 I am transmitting a negative at this point I am doing some sort of a negative pulse kind of thing. That means like this. Okay. So this is your like this. Then again 1 you are transmitting that at 2t. Then say 101. Then here you have again it's the same kind of thing you are transmitting. So this is some sort of a rest cosine field. Okay, rest cosine means your transfer function has some cos square term. Okay, so transfer function has some cos square term. Okay, now these. So that means if I have a rest cosine filter, then we know that means if I do the sampling at t equal to capital T, this is my detection point. If you remember that my detection point is at t equal to capital T. Yes. So you know that there's a t equal to capital T. I am doing the sampling. If I have some sort of a rest cosine filter at this side, then I don't have any ISI effect. Okay, that we have studied. Now let us see. So why there is no ISI effect? Because I have the rest cosine filter is like a much more tapered sinc filter, where actually the zero crossing will be at all symbol times. Okay. Now let us see that how to mitigate this ISI. Okay. Now say I have a total response. Okay, after that means this is your source. Then there's a transmitter channel, transmitter blocks, all sub blocks. Then you have a transmitter front end. Then there's a channel. Then receiver front end. Then your receiver block, and then receiver. Okay. Now the total transfer functions, that means from source to receiver, I am saying that means it is H transmitter. This is H transmitter. Then there's a H receiver. This is H receiver. Okay. Then there's a H channel. Okay, H channel. Now you see when the channel is delta, or either if I have a channel has some transfer function, then what so this HEF I am just designing separate equalizer filter in order to mitigate the effect of HCF. That means that HCF and HEF that should be equal to 1. Okay. If I have that means H equalizer filter will be the inverse of the channel frequency response. Then I have this part, these two are gone. Now I have only this HT and HR. Now if I do this HT and HR, if I have a rest cosine, that is product of these two, if that is a rest cosine kind of. Okay. If the product of these two is if it is rest cosine, that is that cos square that one, then at the output you will have all that damped sinc filter or normal sinc filter, or there is a damped sinc filter, depending on the damping is depending on the value of R, that is roll-off factor, but you don't have any ISI. So that's why that they are saying that I will design my equalizer such that these two terms are gone, and rather HT and HR, that is some sort of I am just assuming this is my rest cosine characteristics. That means RC equal to HT and HR. If this is rest cosine, that means this will be root rest cosine and this will be root rest cosine. Okay, because this is a cos square, that means cos and cos. Okay, so root rest cosine means raised means square, root rest means normal cos. Because this is your cos square filter, this is cos and this is cos. That means sometimes you say that square root of rest cosine filter. Okay, so. And I am saying that equalizer filter that I told that HEF will be 1 by HCF, that is 1 by mod HCF and e to the power minus jθ. Because HCF, that channel I am saying that equal to that mod of HC f into e to the power minus, let's say plus j, say something else here. And say theta c is itself negative. Theta c is itself negative. It's a lag. Okay. So that actually that because they have did it something like this. Anyway, so they have done it like this. So depending on theta, they have defined say HC channel. I have to model in this way, and I will design this equalizer filter like this. So if you see the block diagram, that the very fast block diagram, you can. So that means this is my equalizing filter. You see, now I am trying to do that. This is my equalizing filter. This equalizing filter I have to design it as 1 by mod HCF into e to the power minus j theta, which is the channel's inversion of that. This is my receiving filter. This is HRF, and the transmitter side I have HTF and this HRF. These two are some sort of a rest cosine filter. This is HRF. Okay. So now that's why we say that this is that is Nyquist pulse and the square root Nyquist pulse, or square root means that. And you see that if I have some sort of a filter, some sort of a transmit signal, and then what will happen? If I have some sort of a Nyquist Nyquist condition is made, that means I have some sort of a say a rest cosine kind of characteristic. Rest cosine r may be 0. If r is 0, then it is a normal sync type of rectangular filter with a sync is a time domain characteristic. If r equal to 0.5, r equal to 1, then your the rectangular one will be rectangular frequency response will be like a phosphate type of filter, but your time domain, your sync will be damped. But anyway, whatever may be the case, you see at tau 0, say I have a response something like that. Say for this one, say I am starting from at this point. Okay. So say some sort of a fast one. Okay. Then the next one, then this part, that third one, this part. Now what I am doing at the detector point where I am doing the sampling, I am doing sampling at this point, this point, this point. That means that's why if this is a rest cosine, that means even if the effects are there, but at sampling point I don't have any effect. Okay. So this is the characteristic, and this one is a rest cosine, and one is the transmitter part, and one is the receiver part. That is HT and HR. Now that means so this is some sort of this is the square root Nyquist pulse, and this is the Nyquist pulse. Okay, this is a normal Nyquist pulse means it is. And what is my spectrum? Spectrum was something like this. Okay, and it was that two. That's why that not two. Half. So yes, half part will take the one symbol per second. Yes, because in each second you have the one symbol. That means next one you will transmit. But you see that point is, so that means this is my Nyquist pulse, and if I if I have a square root of this one, that means if I take the transfer function, if you take the transfer function square root and if you take the inverse Fourier transform, then you will have a square root of a Nyquist pulse. And you see that in the Nyquist pulse at t equal to 0, then t equal to say capital T is 1, 2t, 3t. Now you see that at t equal to t, 2t, it is basically doing a zero crossing. Minus t, minus 2t, all this, because it's a pure sync kind of. But you see that in this square root Nyquist pulse at t equal to t, 2t, you see that it is much more going down. It is not doing the zero crossing. At 2t, it is going up. Okay. So that means it is for Nyquist pulse for t time from main low, it is coming 1 to 0. But here that it is coming 1 to something, some amount, some 0.1. It is maybe minus 0. So it is coming. So that means this one is much sharper than the normal Nyquist pulse or rest cosine pulse. Okay, this is some sort of a rest cosine pulse. Rest cosine with r equal to 0. Okay, doing roll up. Anyway, so that means, and you see that means if I do the output of the rest cosine pulses, that means say they are basically with a max filter implementation and delay. So that means it is basically getting that exactly right point. It is doing the same. But if I do the square root, only square root, not the rest cosine, then because actually please remember that HT and HR, individual root rest, you will get a rest cosine. But instead of rest cosine, if you just by mistake, if you send the root rest, then you see that sampling is not matched. Even if you do a t equal to the actual value is this, you are making a mistake. Please read this portion. Please read this portion. This is I am just covering in a hurry. Anyway, so that means we have understood that is channel equalization is required. So that is the two things. One is this, that rest cosine characteristics is to take care of the ISI. Channel equalization is to minimize the channel degradation. There are two independent effects. Okay. Now for that means say I am doing a channel characterization, that is HCF equal to mod HC to the power j theta CF. Okay. Now this one that I told that HT and IHR, they are the rest cosine. That means an individual is the root rest cosine. That is cos and cos. This is basically a cos square. So I have I have to design this equalizer. Now designing this equalizer, so I will come to this later, this idea. Now this equalizer, so what I have to do, that means say I have that means equalizer means I have to design a equalizer filter. First one. The filter is some sort of a transversal structure. Transversal structure means if you remember that we studied this thing, say this type of characteristics, or rather if I take the other picture, then I think that this type. So if you are something like that, I have a input pulse PRT and something like that CN into this, then delay C3, then another delay C minus 2, another delay C minus 1, C minus then C0, C1, C2, C3, and say C7, and finally you are getting a output pulse of PK. Okay. Now you see. So that means this is my equalizer. You see. That means this is my equalizer. The same characteristic. That means you are doing a delay C minus n to C plus n. That means I am putting a delay. After delay, you are just forget at this point. You forget about this. At this point, you don't talk about it. Don't say this connection is not there. Okay. So I will tell you why the connection is. So you are just means summations ckx t minus k minus n kind of thing. That is a delayed input and multiplication with individual coefficients added up. This is called the transversal characteristics of transversal filter. Now the question is, now next you come to this algorithm for coefficient adjustment. Algorithm means of the coefficient adjustment means, let me see, how will you, so that means you try to understand these coefficients, Cn, Cn minus 1, these are basically you are trying to model the channel. Because with this is basically transfer function, which is basically 1 by mod HC f to the power minus j. And when you are multiplying with this channel, because already it is channel degraded, this is the channel degraded input. Channel degraded input, and this is a filter, because the channel degraded input means in the channel I have some HCF into e to the power j theta. Okay. Now say I am this is my channel. Okay. I am designing this portion. Okay. So this effect is getting nullified. It's becoming 1. So that means how I am designing this 1 by HCF to the power minus j theta, just by calculating this C minus n plus 1, Cn minus 1 to Cn. That means I have to somehow calculate this. How will I calculate? That means I will send a known signal, and I know that means say I will get if I send the known signal, and I know if I know that this channel degraded input is this. So channel degraded input means, and with this channel degraded input, I know that what is my actual output. Okay, so that means if I have a known degradation model, so I am putting a known degradation model, and I am getting yk, and then with this yk I am just feeding that, and with this yk I am just trying to tune the thing so that this this known synthetic degradation I can nullify over here. That means what I like to say I have some sort of a, say P is a signal, I have a standard degradation effect, known degradation effect. That means I know that HCF and theta is, and then I am sending over here. I am fine tuning this Cn by some way so that I am getting over again a P. This is my degradation model. That means H and theta, HC theta. So I have got X. From there, this YK is basically again I am trying to get almost, okay, YK is almost. So then you can say that means this Cn basically removes the effect of this H theta and HC and theta C. HC and theta C. So when you are, so that means you have to find, when you have a known sequence, you can do the fine tuning, and once you have done, then you can drop this. Then you can remove this. You need not do that. And when again the channel is degraded in a different way, then again you have to do the fine tuning. This is algorithm for coefficient adjustment. That is from these data, you have some algorithm. I will discuss those algorithms later, and you will fine tune these coefficients. Okay. So that means in a sense, this Cn, C minus n to Cn, they are my, so with this you are doing the inverse modeling of the channel. Okay, that means, okay. Now let us come to that, so that means this is my, so that means these transversal filter, that means transversal filter means basically it's the equalizer, the transversal structure. In this transversal structure you are implementing. And what is my xk? The filter input. If you that means this is my xk. and this one you are basically a transversal filter. Okay, so this is XK means you have a deceiving filter. Then I have, say at this side I have a HTF. Okay, and finally you have got some sort of a transmitted waveform, and then adding it up and all these things. So you have, let me say this is your input. Input HT, HR, then that HT into HR, this is HR, okay? That is I have input, forget about this point. Anyway, this is a frequency translation effect is a linear operator. You can remove this for the time being, and I'm talking about all baseband. So HT into HR, then you have got an equalizing filter. Now you see, that means, say if I have, so this is the input of the equalizer. Now you see that if that is the input of the equalizer means this is my equalizer, or rather this is my equalizer, HE, then I have HR, then this is HT, H channel, then this is the HT. Okay. Say this HT is the input is some sort of a, say X. Okay. And here, now see HT and HR, they are some sort of a rest cosine pair. Okay, that is, this is root rest, the total is rest cosine. Now, if this channel, if it is not, if it doesn't do the any degradation, if it is a delta T, so then what will happen at the equalizer input? You have X and H rest cosine characteristics, and that should be the input. And if it is a rest cosine characteristics, then you are at 0 point you will have the 1, at t equal to capital T all 0, then t equal to 2t, it is a sync kind of thing, 2t to 3t again sync, and similarly here minus t, then 0, then 3t, something like this. But you see that due to this channel degradation, so there is at symbol time there is the, instead of 0 value, it is some amount, minus 0.3, plus 0.2, plus 0.1, something like this. That you don't want. So this is, that means ideally it should be a sync kind of, ideally it should be a sync kind of filter. Okay. So that means sync is sync with cosine characteristics and all these things, but there should not be any effect here, because actually you are doing sampling at this point, you are doing sampling at this point, sampling at this point, sampling at this point, sampling at this point. Now, if I have an effect like this, then the second, say I have 1, then you have sent 1, then you have sent 0. That is 1 means PT, say 0 is say minus PT. So that is you are doing a bipolar pulse kind of. Then at 1 means I have something like this. Say I have a all crossing all this, sorry, all this type of thing. Then what will happen? At this point, first of all, this is 0.9, but the previous ones minus 0.3 is coming into picture. Maybe you don't know the further previous things also have come into picture or not. So that means if I have a pure rest cosine, no channel degradation effect, I don't have any problem. But now I have rest cosine, but still I am facing the problem means at the sampling point. That means the channel is degrading some. Channel has some corruption, and I have to mitigate that one. So in order to mitigate that one, so what I should do, that means what should be my, first I will talk about 0 forcing equalizer. Okay. So what should be my output? My output should be ideally at t equal to 0, it should be 1, then all the output should be 0, something like this. So basically I am trying to, and what is my, so this is my output. So rather what I am doing, that means what is my ZK? ZK is basically something n minus n to plus n, xk minus n cn, that is like this. That means if you can remember that what is my zk or yk, that is xk minus n cn. Let me say c0 p0. If I just break it in this way, that means I have n is from minus n to plus n, and say ki is minus 2n to plus 2n. That means I am taking some step. See, please remember, this is the time window index, and this is a tap index, minus n to plus n. This is the tap index. This is n. Okay, and this k minus 2n to plus. You can take minus 3n to minus plus 4n, anything. Just you can take minus capital. I am taking minus capital K to plus something. Okay, it doesn't matter. Okay, so what will happen in that case? That basically you have this equation quite known to you. That means if I write it in this, instead of z you write y. So now what you can do, or rather if you check from the other one, that means ideally what do you want? Ideally you want, this was my degraded channel degraded signal. That means what is my xt? That means this one is basically this particular characteristics. Okay. Now this should be my output. That means at t equal to say some NTB, at least some forget about NTB for the time being. So say I have all this point all 0. Is 0.1, 0, 0, 0 kind. And why I have put NTB? Because you see that means at t equal to 0 you transmit something. So here at t equal to NTB, t minus NTB, that is TB amount, NTB amount of delay. Okay, because you have minus n to plus n, 2n number of delay block. So that means at the middle you have n number of delay blocks. You see, this is total 2n number of delay blocks. So here it is n number of delay blocks. This one, n number of delay blocks. Okay. So it's maybe n plus 1 or n plus 1. Okay. This is 2n plus 1 number of delay. Now, so that's why basically n plus 1, it doesn't matter. It's whether it is n dB or n plus dB, n minus dB, that doesn't matter anyway. Just that. So the basic point is that my output should be like this. So that means I have no at the sampling point there should not be anything, because say when I am transmitting the pulses at the transmitter side, you see that means if I don't do the equalization, then what will happen? Say I am basically transmitting say 1 1 0. Then what will happen? That and say 1 is PT and 0 is minus. Now PT means same kind of. Then what will happen? 1 is this type of pulse. Then another one. You have another shifted version of this one. Then 0 means shifted by 2 dB, but inverted version, something like this. Now when I have something like that, okay, that this a minus 1, this is also a minus 1. So that means when you are doing the sampling at this point, this point, this will be reduced further only due to this. Again, I have this side. So if there may be a decision problem. Okay. Also there may be a jitter and all this. Okay. But so that's why what I want a zero crossing at symbol time where I am doing the sampling. Now, but you see that what I have to do. That means first, if I just do only, so this is what. Now the point is that if I take only one pulse, say I have, say if I instead of why I have taken many number of this type of factor, many number of coefficients. If I take only one coefficient, C0 into PR. If you do C0 into PR, this C0 is some 0.51, some scalar number. Can you get from PR to P0T? No. Rather, because you need, because finally here you have to make a 0 crossing point. So what I am doing, C0 PT, C0 PRT, C1 PRT minus capital T, C2 PP PRT minus capital, and just I am trying to control C0, C1, C2, C3, all these terms, and C minus 1, C minus 2, so that I will get this out. Okay. So then, so what I am doing, that P0T, instead of earlier I have taken P0T, output is C0 into PRT minus N. Okay. So if you remember that earlier what I have done, this is C0 into PRNT minus T. That means earlier I have done that what is my POT? That is POT. I was trying that, okay, let's see C0 E R T minus N. Okay. Instead of that, what I am doing, that means that I am putting that instead of 1, I am just putting that as sum. Okay, sum, that is C0, instead of C0, I am putting a Cn, n equal to minus n2 plus n. Okay, and I have all this. Okay. Now that, or rather PRT, say I am putting P0T is like this. Now P0T, that I know that what is my P0T? P0T is basically all 0, then in between 1, then all 0. That means what is my P0T? What I am saying, that means P0T is, here it is 0, here it is 1, then here 0, 0, 0. Say that means 1, then say 0, 0, 0. Here also 0, 0, 0. This is 1, 0 in this crossing, 0 in this crossing. So that I am writing. Okay, you see, that means only in between 1, then all 0. And we are writing P0 from there. We are just doing this. If I Cn is my unknown, and I am putting this PRT minus NTB here. PR0, PR minus 1 in this form, and this is my C. Okay, then so you see that this is a known. Okay, P0 is known. I have to calculate C. That is, now what is the dimension of this one? What is the dimension of pure matrix? That is 2n plus 1 by 2n plus 1 square matrix. Now C is unknown. This is unknown. So what I will do, C equal to P inverse P0. Okay. Now say this P inverse, or rather PR inverse. Now what is PR? PR, you see, this is a PR minus 1. This is a Coeplitz's matrix. Coeplitz's matrix means they will be, you see, that 2n minus 1 PR 2n. PR, that means Coeplitz's matrix is something like this. A0, A0, A0. Say I have 3 cross here, like A1, A2, say A3, A3, A4, A1, A2. You see? So Dweck matrix is absolutely defined by the first row and first row. That means if you know A0, A1, A2, A3, A4, then everything you know. Okay. So you need not know everything. If you say if it is a, so that means that it is 2n plus 1 into 2n plus 1, but actually you have to know this 2n plus 1 plus 2n plus 1 minus 1. Okay, because minus 1 is the first element you know. Okay. So instead of in the Dweck matrix, though actually ideally you should have 2n plus 1 into 2n plus 1 into, but actually you have to know only because 2n plus 1 plus 2n plus 1 minus 1. It is 4n plus 1 number of rather 4n plus 1 number of elements. That means this one you have to know and this one. Anyway, so and for this Dweck matrix, the inversion there are you need not do the actual that normal inverse the way we do. Actually, there are certain computationally easy technique to do this inverse of Dweck matrix, and then you multiply with P0. Now multiply with P0 means as P0 is 0 0 all 1 0. That means if I do some basic say PR is D, PR inverse is D. So that means say I have a V1, V11, V12, V13. So similarly V21, V22, V23. But I multiply with 0, 1, then what will happen? Say I am doing V21, V31, V22, V23, V32, V33. Basically, when you, so this is basically PR inverse. Say I am doing. Now, if I do a 0, 1, 0 multiplication, means what you have to do? That means this is a vector. Okay, this vector will be that first element 0, then V12, then 0. That means what you have to do? That second one, actually, basically, only you need not do this multiplication. You have to only take out this. Okay, because if you multiply that V1, V21, V22. Okay, just you take out after inversion, you take out this one. Okay, this is called a zero forcing equalizer. Why the name zero forcing? Because you are forcing that your equalizer output at t equal to TB, 2 TB, 3 TB, is n plus 1 TB, n plus 2 TB. There it should be 0. Okay. Now that there's an example that you can solve it. Next, we will talk about, maybe Monday we will talk about the minimum mean square equalizer. There's another equalizer. In this equalizer, rather what we will do, instead of here, you see that here we have taken 2n plus 1 cross 2n plus 1. That means 2n plus 1 cross 2n plus 1. Now, what is this 2n plus 1? That means I have taken the data point at 2n plus 1 number of points. That means what you have done, this P0T, and you are getting P0T equal to K at sampling point ATP, and K you have, and finally you have removed this T. That means you are solving this equation, and here you have taken this K equal to 0, K equal to plus minus 2, K plus minus. You have taken K equal to plus minus K up to this. So that this side you have. So that means that P matrix you have got 2n plus 1 number of equation, 2n plus 1 number of entry. Then okay, that middle one is 0, rest all are 0. Then I have this PRK minus 1. K and n both are varying. N is varying from minus n to plus n. K is also varying minus n to plus n. So you have got a square matrix, that is that square matrix is that PR matrix. Okay, so and then you have got Cn is basically a vector of 2n plus 1, that is C minus n to C plus n. Instead of that, if I take up something instead of plus minus n, if I take something plus minus n. Okay. So that you will have 2k plus 1, and I am assuming that k is basically greater than it. Then what about this matrix? This matrix will be 2k plus 1 cross 2n plus 1. This dimension, and k is greater than n means this is basically a tall matrix. Now then I have a recessive delta. Okay. And this is your PPGO. Now when I have a tall matrix, then I cannot do the inverse. I do Moore-Penrose inverse or Sibu inverse. That we will talk about next class. Not talk about this on Monday. Thank you. Hello? কি বলছো? এবার কথা বলবো।